In a dark corner of our galaxy, 40 light-years from Earth, there exists a planetary system that has fascinated astronomers around the world. Is it possible that, in the vastness of space, there are other worlds where life, as we know it, or in completely unexpected forms, has found refuge? The Trappist-1 system, with its 7 Earth-sized planets orbiting a small cold star, has become the greatest enigma of modern astronomy. What secrets await in these 7 sibling worlds, and why have they captured the imagination of scientists and dreamers alike? The discovery of Trappist-1 marked a turning point in the search for exoplanets. Never before had a system with so many rocky planets been observed, all so close to their host star, and, at the same time, so comparable to our own planet in size and composition. The idea that 7 spheres, similar to Earth, revolve in a delicate gravitational balance is as perplexing as it is exciting. What conditions prevail on their surfaces? Could any of them harbor oceans, dense atmospheres, or even conditions suitable for life? The compact nature of the system, where all the planets could fit within the orbit of Mercury, challenges our intuition about how worlds should be organized around a star. Imagine a cosmic neighborhood where the planets are so close to each other that a hypothetical inhabitant could observe several sibling worlds dominating the horizon, much larger and brighter than any planet we see from Earth. How does this proximity affect their climates, their geology, and above all, their chances of being inhabited? Trappist-1 invites us to rethink what we know about the formation of planetary systems. It forces us to ask whether life could thrive in environments radically different from ours, and whether, in some corner of those 7 orbs, conditions exist that could one day answer one of humanity's oldest questions. Are we alone in the universe? Today, we will dive into the mysteries of this system and explore what makes each of these 7 sibling worlds so special. Trappist-1 is a name that, at first glance, might seem like it came out of a science fiction work, but it actually corresponds to one of the most fascinating planetary systems discovered so far in our galaxy. Why is it called that? The name Trappist comes from a specialized telescope, the Transiting Planets and Planetesimals Small Telescope, whose acronym in English is Trappist. The Belgian scientists who operated this telescope chose the name as a nod to the famous Trappist beer from their country. The number 1 indicates that it is the first system of great interest found by this instrument. Thus, Trappist-1 is both a tribute and a scientific designation. But where is this system located in the vast universe? Trappist-1 is located in the constellation Aquarius, about 40 light-years from Earth. 40 light-years may sound close in cosmic terms, but to put it in perspective, if we could travel at the current speed of the fastest probes ever launched by humanity, it would take us hundreds of thousands of years to get there. Still, for astronomers, Trappist-1 is practically around the corner in our galactic neighborhood. The story of its discovery is as surprising as its name. For a long time, astronomers had been searching for exoplanets, planets outside our solar system, around sun-like stars. However, it was by observing much smaller and cooler stars, like Trappist-1, that something unexpected appeared. Not 1, but 7 Earth-sized planets orbiting the same star. This finding was announced in 2 stages, first with the discovery of 3 planets in 2016, and then, in 2017, with the confirmation of 4 more. The news caused a real stir in the scientific community and captured the imagination of the global public. What makes this system so special? Unlike most known systems, Trappist-1 hosts 7 planets similar in size to ours, all in compact orbits around a tiny, cool star. It's as if our solar system had only Earth-like planets, all orbiting very close to their sun. This makes Trappist-1 a natural laboratory for studying the formation of rocky worlds, and perhaps the possibility of life beyond our neighborhood. The discovery of Trappist-1 not only expanded the catalogue of exoplanets, but also changed the way we search for new homes in the cosmos.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this star odyssey.
What makes the star Trappist-1 so special? To begin with, we are not talking about a star like the Sun. Trappist-1 is what astronomers call an ultra-cool dwarf. Why such a peculiar name? Simple. Its surface temperature is only about 2,500 degrees Celsius, much lower than the nearly 6,000 of the Sun. If the Sun were a blazing campfire, Trappist-1 would be like a dim but persistent ember, emitting a barely perceptible reddish glow from a distance. But what does it mean to be an ultra-cool dwarf? One of the first differences is its size. Trappist-1 has only about 12% of the Sun's mass, and a radius similar to that of Jupiter. In other words, if our Sun were a beach ball, Trappist-1 would be like a tennis ball, much smaller and lighter. This star is also much less luminous. It emits only a tiny fraction of solar light, just enough to illuminate its nearby worlds. Is it possible for such a small star to support such a rich planetary system? Surprisingly, yes. Its low luminosity means that the so-called habitable zone, where liquid water could exist, is much closer to the star. This causes all its planets to be clustered in extremely compact orbits, almost as if they were trains circling very close around a dim lamp in the dark. That proximity is possible precisely because the radiation and heat from Trappist-1 are much less intense than those of the Sun. Another fascinating curiosity is its longevity. Ultra-cool dwarfs like Trappist-1 consume their nuclear fuel so slowly that they can live trillions of years, much longer than the Sun itself. This opens up a range of possibilities for the formation and evolution of complex planetary systems around it. Could these worlds have had enough time to develop stable conditions and perhaps life? The answer is still a mystery, but the serene and enduring nature of Trappist-1 makes it one of the most intriguing stars in the cosmic neighborhood. How is it possible that over 40 light-years from Earth, astronomers have discovered a planetary system with 7 worlds? The story of the discovery of Trappist-1 is a fascinating example of scientific ingenuity and perseverance. It all began with the desire to search for planets outside the solar system, the so-called exoplanets, especially around small, cool stars, where the possibility of finding worlds similar to ours increases. Trappist-1, an unremarkable star in the constellation Aquarius, was just one among millions, but its size and dim brightness made it an ideal target for planet hunters. Who took the first step to unveil this mystery? The credit goes to an international team led by Belgian astronomer Michael Gillen. Using the TRAPPIST telescope located in Chile, the group began to observe tiny dips in light coming from the star. These dips, although minuscule, were like the fingerprints of planets passing in front of their parent star. But how could they be sure? It wasn't enough to detect a decrease in brightness. They needed to decipher whether these signals repeated with the necessary regularity to indicate the presence of planets. Patience was key. For several months, the team carefully recorded every light variation. Soon, they confirmed the existence of 3 planets. But the story didn't end there. With the help of more powerful telescopes, such as the VLT in Chile and NASA's Spitzer, astronomers discovered that those 3 worlds were just the beginning. In a move worthy of a detective, they combined data from different observatories around the world and, as if piecing together a puzzle, revealed the existence of 7 planets in total. Each produced its own subtle eclipse, interleaved in an almost choreographed orbital dance. And why did this discovery surprise the scientific community so much? Because it was not an ordinary system. 7 planets similar in size to Earth, orbiting an ultra-cool dwarf star, is something that had never been seen before. The news broke in February 2017 and captured the imagination of the entire world. Trappist-1 immediately became one of the most studied and promising planetary systems in the search for life beyond our cosmic neighborhood. How is it possible to discover planets orbiting distant stars, many light years away from Earth, when we can't even see them directly? The answer lies in one of the most ingenious methods of modern astronomy: the transit method. This method is based on a simple yet powerful premise. When a planet passes in front of its star as viewed from our perspective, it blocks a small fraction of that star's light. It's like a mosquito passing in front of a lit bulb. You wouldn't see the mosquito in detail, but you would notice a brief decrease in the intensity of the light. But how is such a subtle signal detected? Astronomers use telescopes equipped with extremely precise instruments capable of measuring tiny changes in the brightness of stars. If that decrease in light occurs periodically and follows the same pattern, it's a strong clue that a planet is orbiting its star and repeatedly crossing in front of it. This phenomenon is known as planetary transit and is the cosmic equivalent of seeing the shadow of an object pass in front of a lamp, except the lamp is a star millions of kilometers away, and the object is a planet. Why is the transit method so valuable for studying systems like Trappist-1? Because it not only allows us to confirm the presence of planets, but also to measure their size. The amount of light that decreases tells us how large the planet is compared to its star. If the drop in brightness is small, the planet is small. If it's larger, the planet is bigger. Furthermore, if we combine this data with the time it takes to complete its orbit, we can calculate the distance at which it is from its star. It's like reconstructing someone else's solar system just by observing the shadows of their planets. Another fascinating advantage of the transit method is that when a planet has an atmosphere, part of the star's light passes through that layer of gases before reaching us. By analyzing that light with spectroscopy, researchers can identify the chemical components of the planet's atmosphere. Elements like water vapor, methane, or carbon dioxide leave unmistakable traces. Thus, the transit method not only reveals the existence and size of exoplanets, but also opens a unique window to study whether they could harbor conditions suitable for life. Who would have imagined that a simple drop in the brightness of a star could tell us so much about such distant worlds? What are the 7 worlds of Trappist-1 really made of? This question has intrigued astronomers around the world since their discovery. Unlike gas giants like Jupiter and Saturn, the planets of Trappist-1 are mostly rocky, very similar to Earth, Venus, or Mars. But how do we know this if we have never been there? The key lies in combining the information obtained about their sizes and masses, allowing scientists to calculate their density. If the density is high, like that of Earth, it is concluded that the planet is mainly composed of rock and metal. If it is low, it could be a world dominated by gases or ice. By analyzing the data from the transits and the small variations in the star's movement caused by the gravity of the planets, it has been determined that all the planets of Trappist-1 have a density consistent with a rocky composition. Imagine holding in your hands 7 marbles, all with a solid core, a mineral crust, and perhaps a thin layer of gases surrounding them. But, although they share that rocky base, each could have unique ingredients on its surface or atmosphere, such as water, carbon dioxide, or even ice. Could some of these worlds have active volcanoes, huge underground oceans, or layers of perpetual ice? Surprisingly, the diversity of these exoplanets goes beyond their simple rocky composition. The differences in density among the 7 suggest that some could have more water than Earth, while others would be drier and more arid. For example, if one of these planets had the same water ratio as Earth, it would already be a strong candidate for harboring conditions favorable to life. However, there are indications that some could be covered by oceans, or, conversely, be inhospitable deserts of rock and dust. Is it possible to find a world with endless seas, or perhaps a planet where most of the water is trapped beneath a thick layer of ice? The composition of these planets not only reveals fascinating data about their formation, but is also crucial for understanding their potential habitability. A rocky planet with the right amount of water and a protective atmosphere could offer a conducive environment for life as we know it. Therefore, studying the composition of the exoplanets of Trappist-1 is not just a matter of scientific curiosity, but a quest to answer one of humanity's deepest questions. Are we alone in the universe? Or are there other rocky oases waiting to be discovered? What would happen if all the planets in the solar system were so close together that they could fit within the orbit of Mercury? That is exactly what happens in Trappist-1. The orbits of its 7 exoplanets are so compact that, compared to our system, they seem to be literally squeezed next to each other. No planet is farther from its star than Mercury is from the Sun, and yet, there are 7 completely distinct worlds. Why does this happen? The answer has to do with the star Trappist-1 itself, which is much smaller and cooler than our Sun, allowing the planets to be closer without being scorched by radiation. To understand the scale, just think of a running track. Imagine that the Sun and Neptune are separated by the length of a football field. In Trappist-1, all 7 planets would be clustered in the arch zone, almost shoulder to shoulder. The distances between them are so small that if you were standing on the surface of one of these worlds and looked up at the sky, you could see the other planets as huge disks, much larger and brighter than the Moon from Earth. Is this common in the universe? Surprisingly, no. Most known planetary systems have planets that are much more spread out. The configuration of Trappist-1 is unique and raises fascinating questions. Can these worlds survive for billions of years in such a congested environment? How do their proximities affect the stability of their orbits? Scientists have discovered that the extreme compactness of this system has been made possible by complex gravitational interactions and a kind of orbital dance that prevents the planets from colliding with each other. Another curiosity is the time it takes for each planet to complete one full orbit around the star. While on Earth, a year lasts 365 days, in Trappist-1, years can be as short as a day and a half, or as long as just over a week. This dizzying speed is precisely due to the compact orbits and the low mass of the star. The result is a system where everything happens at high speed, but in such a delicate balance that any small change could alter the fate of these 7 sibling worlds. Could such a dense system ever harbor life? That is one of the big questions that still remain unanswered. What do the planets of Trappist-1 have in common with a perfectly tuned orchestra? Although it may seem incredible, these 7 worlds dance around their star following a harmonic pattern, a kind of cosmic score where each planet sets the rhythm for the others. This synchronization is called orbital resonance. Why is it so important? Because it means that the planets not only orbit close to each other, but they also do so in mathematically related cycles, as if each one knows exactly when to turn to avoid colliding with the others. To understand it better, let's think about swings in a park. If you push several children on different swings, but you make their movements match, you'll notice that they never bump into each other and achieve a constant and predictable rhythm. In Trappist-1, the planets are pushing against each other gravitationally, adjusting their orbits with surprising precision. For example, every time one of the planets completes a certain number of orbits around the star, its siblings have also completed an exact number of orbits. This phenomenon prevents gravitational forces from destabilizing the system, allowing the planets to stay together for billions of years. But how does this resonance work in detail? In the case of Trappist-1, the 7 planets form a chain of multiple resonances. That is, the orbits of almost all of them are so synchronized that for every 2, 3, or even 4 orbits of one planet, another completes a different amount, but always following an exact proportion. This orbital gear is so precise that if one of the planets were to change its speed even slightly, the entire system could lose its balance, and some worlds would be ejected from the system or end up colliding with each other. Thus, resonances are not only curious, but vital for the survival of all these sibling worlds. Now, what are the consequences of living in such a tightly adjusted system? Orbital resonances cause the planets of Trappist-1 to experience slight periodic gravitational tugs, which can generate heat within them. This phenomenon, known as tidal heating, could be key to maintaining geological activity or even favoring the presence of liquid water beneath the surface on some of these planets. Additionally, the stability of the orbits makes it easier to predict transits and eclipses, helping astronomers study their characteristics with a level of precision that is hard to achieve in other planetary systems. Ultimately, the orbital resonances in Trappist-1 turn this system into a unique natural laboratory for understanding the dynamics and evolution of distant worlds. What makes Trappist-1b special? When astronomers discovered this planet, the first thing that caught their attention was how close it orbits its star. To put it in perspective, if Trappist-1b were in our solar system, it would be much closer to the Sun than Mercury. Its year lasts just a day and a half on Earth. That is, if you lived there, you would celebrate your birthday every little more than 36 hours. This proximity means it receives almost 4 times more radiation than Earth. Is Trappist-1b similar to Earth? In terms of size, yes. Its radius is about 1% larger than that of our planet, and its mass is similar, suggesting a rocky composition. However, the conditions on its surface would be very different. Its estimated temperature, even if it had an atmosphere similar to Earth's, would exceed 200 degrees Celsius. This makes it a world too hot for life as we know it. Could liquid water exist on Trappist-1b? The answer, for now, is unlikely. The high temperatures would cause any water present to evaporate quickly. Additionally, the intense radiation from the star could hinder the existence of a dense and stable atmosphere. Without sufficient atmospheric protection, the planet's surface would be exposed to severe erosion and constant stellar winds, making this environment even more inhospitable. Is there anything that makes Trappist-1b fascinating for science? Absolutely. Despite its extreme conditions, this planet is crucial for understanding how rocky worlds interact with ultra-cool dwarf stars. Studying its atmosphere, composition, and orbital behavior helps scientists refine their models of planet formation and better understand the limits of habitability in other solar systems. In a way, Trappist-1b is the perfect natural laboratory to explore the extremes of rocky planets beyond our cosmic neighborhood. What makes the planet Trappist-1c so special within this fascinating system of 7 worlds? Trappist-1c is the second planet in order of proximity to its star, orbiting much closer than Mercury does to the Sun. However, because the Trappist-1 star is an ultra-cool dwarf, this planet does not become a scorching hell. Can a planet so close to its star be compatible with life, or at least with less extreme conditions? The answer lies in its particularities. Trappist-1c is just a bit larger than our own planet, with a radius approximately 10% greater than that of Earth. However, its mass is almost the same, suggesting a rocky composition, although slightly less dense than Earth. Why is this relevant? Because a lower density could indicate the presence of lighter materials or even a thin atmosphere, although so far no dense atmosphere has been detected on this planet. Current models suggest that if any atmosphere exists, it is likely very thin, perhaps similar to that of Mars. Regarding temperature, Trappist-1c is a cold world compared to what we would expect from a planet so close to its star. Estimates place its surface temperature around -110 degrees Celsius, depending on the type of atmosphere it possesses. This figure may seem inhospitable, but it is considerably less extreme than that of Venus or Mercury in our solar system. Could it harbor liquid water? With such cold, water, if it exists, would be in the form of ice. Although some scientists believe that internal geothermal processes could create warmer niches beneath the surface. One of the most intriguing curiosities of Trappist-1c is its orbital relationship with the other planets in the system. Their orbits are so perfectly synchronized that every so often Trappist-1c and its neighbors pass close to each other, producing gravitational pulls that stabilize their trajectories. This synchronicity is comparable to a cosmic dance where each planet follows the rhythm without ever stumbling. Although Trappist-1c is not the most promising candidate for life as we know it, its study is essential for understanding how compact planetary systems work and how the diversity of worlds can challenge our ideas about where life might arise. What makes the planet Trappist-1d so special? This world occupies a privileged position within the system. neither too close nor too far from its parent star. If we compare it to a relay race, Trappist-1d is the third runner. Right at a critical point where scientists believe the necessary conditions for the presence of liquid water, one of the key ingredients for life as we know it, could exist. But could there really be oceans or lakes on its surface? The answer, for now, is a fascinating enigma that keeps the scientific community on edge. Trappist-1d also stands out for its size. It is just slightly smaller than Earth, with a radius approximately 72% that of our planet. Its mass, on the other hand, is almost half that of Earth. This suggests that it is a rocky world, meaning its surface could be composed of solid materials rather than gas, like the giants of the solar system. What does this imply in terms of habitability? A rocky planet with enough gravity to retain an atmosphere could host active geological processes and potentially protect water from evaporating into space. The surface temperature of Trappist-1d is one of the most debated aspects. It receives about 4% of the light that Earth receives from the Sun, placing it at the inner edge of the habitable zone of the system. If it had an atmosphere similar to Earth's, its temperature could allow for the existence of liquid water, at least in certain regions. However, if it lacks a dense atmosphere, temperatures could be too extreme, and any water would freeze or evaporate quickly. Here arises a key question. To what extent does the atmosphere, if it exists, help maintain stable conditions on the surface? Another intriguing point is the possibility of liquid water beneath the surface. Some models suggest that while the side permanently exposed to the star could be too hot and the opposite side too cold, a twilight strip between both zones could have moderate temperatures. This is reminiscent of the eternal twilights of some science fiction worlds, where life, if it exists, would cling to that thin line between perpetual day and night. The presence of liquid water, whether on the surface or beneath an ice layer, will largely depend on the characteristics of its atmosphere and internal geological activity, two mysteries that still await resolution through future observations. Will Trappist-1 be a dry and barren world, or a hidden blue gem 40 light-years away? For now, its potential continues to fuel hope for finding a truly habitable environment beyond the solar system. What makes the planet Trappist-1e so special within this intriguing stellar system? For astronomers, Trappist-1e is the crown jewel. It is considered the planet with the greatest potential for habitability among the 7 siblings. Its size and mass are surprisingly similar to those of Earth, which means that if we could stand on its surface, we would feel gravity almost identical to that of our planet. But is this enough to consider it a candidate for hosting life? The density of Trappist-1e indicates that it is a rocky world, not a gas giant, or a planet entirely covered by deep oceans. This detail is crucial, as it increases the chances that its surface is solid and can retain a stable atmosphere. Now, what zone does it orbit within its system? Trappist-1e is precisely in the habitable zone of its star, that special band where the temperature could allow for the existence of liquid water. In cosmic terms, it's as if the planet is in the sweet spot, neither too close nor too far from its star. One of the most fascinating aspects is its estimated surface temperature. Calculations suggest that if Trappist-1e has an atmosphere similar to that of Earth, it could register temperatures suitable for life as we know it. But here arises a big question. Does it really have an atmosphere? So far, telescopes have searched for signals of gases like carbon dioxide or water vapor, but there is still no definitive confirmation. The absence or presence of an atmosphere would completely change the fate of this planet. Without a protective layer, its surface could be battered by stellar radiation, while a suitable atmosphere could regulate the climate and protect any potential form of life. Could liquid water exist on Trappist-1e? The odds, according to current models, are not negligible. If the planet has a sufficiently dense atmosphere, water could persist in liquid form, just like on Earth. However, there is also the possibility that water is trapped beneath a layer of ice if the climate were too cold. or that it evaporates quickly if the atmosphere is too thin. Every small piece of data about Trappist-1e is a piece of a huge puzzle, and solving it would give us invaluable clues on how to search for life in other corners of the universe. Thus, Trappist-1e is not just another exoplanet on the list. It is one of the most promising places outside our solar system to find conditions similar to our own world. Its combination of size, density, and location makes it a natural laboratory for studying planetary evolution and the possibility of life beyond Earth. Although many questions remain, each new observation brings us one step closer to answering the eternal question: are we really alone in the cosmos? What makes a planet like Trappist-1f so special that it captures the attention of astronomers worldwide? This world, the sixth in order of distance from its star, has become the subject of intense studies due to its unique characteristics within the Trappist-1 system. Trappist-1f has a size and mass very similar to that of Earth, making it a fascinating candidate for the study of potentially habitable planets outside the solar system. However, the real intrigue arises when we examine its temperature and the possibility of it retaining an atmosphere. At first glance, one might imagine that a world so far from such a weak star would be completely inhospitable, frozen, and devoid of life. But the distance in Trappist-1 is not measured the same way as in our own solar neighborhood. Trappist-1f orbits much closer to its star than Earth does to the Sun, completing a full orbit in just 9.5 days. Despite this relative proximity, it receives a significantly lower amount of energy than Earth, placing its estimated surface temperature around -35 degrees Celsius. Is this enough to maintain liquid water on its surface? It all depends on the presence and thickness of its atmosphere. The mystery of Trappist-1f's atmosphere is one of the great enigmas of current science. If this planet has a dense atmosphere rich in greenhouse gases like carbon dioxide, it could retain enough heat to allow for the existence of liquid water, at least in certain areas or during certain times. However, if its atmosphere is thin or practically non-existent, the cold would be extreme, and any water, if it exists, would be confined to ice or underground. Astronomers use precise observations of transits and spectroscopic techniques to search for clues, but for now, the thickness and atmospheric composition of Trappist-1f remain unconfirmed. Could this planet then be a refuge for life? The answer is not straightforward. A crucial factor is the planet's ability to shield itself from radiation and retain its atmosphere against the stellar winds of its small star. Additionally, temperature and pressure conditions must be stable enough to allow for the formation of oceans or lakes, even if they are underground. Trappist-1f sits right on the edge of what we consider the habitable zone, and its study helps us expand the definition of habitability beyond traditional Earth parameters. Each new observation brings this world a little closer to the center of the discussion about where and how life might arise in the universe. What makes the planet Trappist-1e so special? For many astronomers, this world is one of the most fascinating in the Trappist-1 system. Its mass and size are comparable to those of Earth, which immediately raises the question, could this planet be a distant twin of our home? Trappist-1e has about 1.5 times the mass of Earth, and its radius is just slightly larger than that of Earth. This means that if we could somehow walk on its surface, we would notice a gravity very similar to what we experience here, which would greatly facilitate human adaptation compared to other giant or too small exoplanets. Now, how do we know that Trappist-1e is rocky and not a gas giant like Neptune? Thanks to meticulous observation of its transits across its star, scientists have calculated its density, which fits perfectly with that of a planet made mainly of rock and metal. This characteristic makes it one of the most promising exoplanets in the search for life, as rocky planets are the only ones we know so far that can host seas, mountains, and stable atmospheres. And what about its temperature? Trappist-1e orbits at a distance that places it in a potentially temperate zone. If it had an atmosphere similar to ours, the temperature on its surface could allow for the presence of liquid water. Of course, this is an assumption based on models, because we still do not know for sure if this planet has a dense atmosphere, or if it is completely exposed to space. However, the possibility that it could have oceans or lakes is enough to keep the attention of the international scientific community. The relevance of Trappist-1e goes beyond its potential habitability. Its location, right on the outer edge of its star's habitable zone, makes it a natural laboratory to study how various factors such as stellar radiation, atmospheric composition, and gravitational interaction between neighboring planets influence the evolution of Earth-like worlds. Could life develop under conditions so different from those in our solar system? Each new piece of data about Trappist-1e brings us a little closer to answering one of humanity's oldest questions. Are we alone in the universe? What mysteries does Trappist-1h, the most distant planet of the 7 siblings, hold? Trappist-1h is, in many ways, the great enigma of the system. Located at the outer edge of the family, this planet orbits at such a distance that it receives only a fraction of the light and heat from its star compared to its closer siblings. If we compare it to our solar system, Trappist-1h would be much closer to its star than Mercury is to the Sun. But the ultra-cool dwarf star is so dim that the surface of Trappist-1h likely remains in perpetual twilight, with temperatures estimated to be below 120 degrees Celsius. How can a world survive under such extreme conditions? One of the big questions is the presence of water. Could Trappist-1h harbor oceans beneath a thick layer of ice, like moons such as Europa or Enceladus? Scientists suspect that, due to its low temperature, the water on the surface would be completely frozen. However, if the planet has an internal heat source, such as geothermal activity or tides caused by gravitational interaction with its neighbors, it is not ruled out that liquid water could exist underground. This possibility sparks enormous interest because, in our own solar system, subglacial environments are considered potential refuges for life. But what do we really know about the atmosphere of Trappist-1h? So far, the data has not confirmed the presence of a dense atmosphere. If it existed, it could act as a protective cloak, trapping some of the scarce stellar heat and preventing the planet from becoming even colder. Conversely, if it lacks a significant atmosphere, Trappist-1h would be an exposed world, where ice dominates the surface and cosmic radiation penetrates unobstructed. This uncertainty makes Trappist-1h a natural laboratory for studying the limits of icy planets and their potential to maintain habitable conditions. Could life find a foothold in such a hostile environment? The answer, for now, is a great mystery. On Earth, extremophiles have shown that life can thrive in conditions that once seemed impossible, beneath kilometers of ice, near hydrothermal vents, or in the driest deserts. If Trappist-1h has a subterranean ocean protected by ice, perhaps in its depths, there could be niches where life has found a way to endure. For this reason, Trappist-1h represents not only a challenge for astronomers, but also a fascinating window into what might be possible on worlds beyond our own. What does the habitable zone really mean? It's a term that sounds almost like science fiction, but in reality, it refers to a very specific region around a star. It's called that because it's the range of distances where conditions allow for the existence of liquid water on the surface of a planet, a fundamental ingredient for life as we know it. But why is liquid water so crucial? Water acts as a universal solvent, facilitating chemical reactions essential for biological processes. Without it, the chemistry of life, at least in the earthly sense, would be practically impossible. Now, in the case of Trappist-1, the habitable zone is much more compact than that of our solar system. This is because the central star is an ultra-cool dwarf, much less luminous than the Sun. Imagine that instead of an intense campfire, you have a small candle. Planets that want to enjoy a temperate climate must be much closer to that candle to receive the right amount of energy. Surprisingly, in Trappist-1, several planets fall within this special range. But which are those lucky worlds? scientists have calculated that at least 3 of the 7 planets of Trappist-1 are completely within the habitable zone. Trappist-1d, Trappist-1e, and Trappist-1f. These planets receive an amount of energy from their star similar to what Earth receives from the Sun, opening up the fascinating possibility that they could harbor liquid water on their surface. There are even debates about whether planet G, a bit farther away, could also meet favorable conditions, especially if it has a dense atmosphere capable of retaining heat. However, being in the habitable zone does not guarantee oceans and rivers. It's just the first condition in a long list of requirements for life. Factors such as atmospheric composition, the presence of a magnetic field, and climate stability also play fundamental roles. Still, the mere fact that several sibling planets orbit together in this golden strip makes Trappist-1 an unprecedented natural laboratory. The key question remains open. Will the right distance be enough for life to emerge? Science is just beginning to investigate the mysteries of these worlds, challenging our imagination and expanding the limits of what is possible in the search for life beyond Earth. Have you ever wondered what it would feel like to step onto the surface of a planet in another star system? The surface temperatures of the planets in Trappist-1 are one of the key factors in determining whether they could harbor life. But how cold or warm are these worlds really? Unlike the planets in our solar system, which receive energy from our Sun, the 7 siblings of Trappist-1 orbit a much cooler and dimmer star. This means that, although they are much closer to their star than Earth is to the Sun, the energy they receive is, in some cases, barely enough to maintain temperatures that could allow for the existence of liquid water. Scientific estimates, derived from models and observations, reveal a fascinating range of temperatures on these exoplanets. For example, Trappist-1b, the closest to the star, experiences surface temperatures that could exceed 100 degrees Celsius in the absence of an atmosphere, making it as inhospitable as a fully functioning oven. On the other hand, Trappist-1h, the farthest planet, has estimated temperatures below 100 degrees below zero, comparable to the icy landscapes of the most distant moons in our solar system. Between these extremes, planets C, D, E, F, and G exhibit temperatures that vary greatly, depending on whether or not they have atmospheres capable of retaining heat. But why is surface temperature so important? Because it defines whether a planet can maintain water in liquid form, one of the essential ingredients for life as we know it. Scientists calculate these temperatures by considering the distance to the star, the amount of light they receive, and above all, whether there is any atmosphere that allows for a greenhouse effect. Imagine a covered pot and an uncovered one over a fire. The covered one retains more heat. Thus, an atmosphere could raise the surface temperatures of some of these planets, making areas where water would freeze actually temperate and friendly to life. Temperature differences also create a range of possible landscapes, from scorching deserts to frozen tundras, passing through temperate regions that could resemble Earth. However, there are still great unknowns. Could some of these planets have oceans beneath ice layers, like those found on Europa, Jupiter's moon? Or perhaps there are dense atmospheres that soften extreme temperatures? Each new observation adds pieces to the puzzle, bringing us closer to understanding whether the 7 sibling worlds of Trappist-1 are simply cold, barren rocks, or if any of them hide the secret of a benign climate capable of harboring life. Could there be liquid water on any of the 7 siblings of Trappist-1? This is one of the most fascinating questions in modern astronomy. Liquid water is considered the essential ingredient for life as we know it, and its presence on an exoplanet could forever change our perception of the universe. But how likely is it that we will find oceans, lakes, or even simple puddles on one of these distant worlds? To answer this question, scientists have closely analyzed the conditions of each planet in the Trappist-1 system. We know that some of them orbit within what is called the habitable zone, meaning at a distance from their star where temperatures would allow water to remain in a liquid state, neither frozen nor evaporated. However, Being in the habitable zone does not guarantee the existence of liquid water. It's like having a cake recipe, but not knowing if you have the ingredients. For water to flow on the surface, it is also necessary for the planet to have a suitable atmosphere, with enough pressure and protection against stellar radiation. What evidence do we have so far? Density analyses suggest that several of these planets, particularly Trappist-1d, E, and F, could have compositions compatible with the presence of water. For example, their masses and radii indicate that they are not completely rocky, which opens the possibility that they contain large reserves of water, perhaps in the form of oceans or ice layers. Some models even propose that these planets could be more watery than Earth itself, with seas covering most of their surface. However, there is a significant obstacle. The intense radiation from the Trappist-1 star could have evaporated some of the original water, especially on the closer planets. On the other hand, on the more distant worlds, the extreme cold could have frozen the water, creating vast glaciers or ice layers similar to what is observed on the icy moons of our own solar system. Therefore, scientists believe that the best bet for finding liquid water lies in the planets located at just the right point, neither too close nor too far from their star. The possibility of liquid water on Trappist-1 is not just a curiosity. If one of these planets harbors oceans, we could be looking at the perfect scenario for the emergence of life, at least in theory. For now, the best tools for searching for signs of water are spectroscopic observations, which analyze the light passing through the possible atmospheres of these worlds. Although water has not yet been conclusively detected, each new observation brings us a little closer to the definitive answer. Could Trappist-1 be the first system where we find seas on another world? The search continues, and the mystery remains open. What makes a planet capable of hosting life? One of the most important keys lies in its atmosphere. Atmospheres not only envelop planets like a protective blanket, but they also regulate temperature, filter out harmful radiation, and, in some cases, allow for the existence of liquid water. But what do we really know about the atmospheres of the 7 planets surrounding Trappist-1? Is it possible that any of these worlds have an atmosphere similar to Earth's? Or are we facing completely strange and hostile environments? So far, scientists have used advanced space telescopes to search for signs of atmospheres on these exoplanets. The main method involves observing the faint dimming of starlight when the planets pass in front of it. If a planet has an atmosphere, some of the starlight filters through its gases, leaving a sort of fingerprint that astronomers can analyze. However, the results have been intriguing and, at times, perplexing. For several of the planets, especially those closest to the star, dense atmospheres like Earth's have not been detected. This suggests that, in these cases, stellar radiation and solar wind may have swept away any light gases, leaving behind bare worlds exposed to the vacuum. But the story doesn't end there. For the planets located in the so-called habitable zone, the situation is much less clear. Could these planets have retained denser atmospheres rich in carbon dioxide, nitrogen, or even water vapor? Some models suggest that a thick enough atmosphere could protect the surface from extreme cold and keep water in liquid form. However, confirming the presence of such atmospheres is no easy task. It requires almost unimaginable precision to detect chemical signals from over 40 light-years away. So far, the available data only allows us to rule out very extensive atmospheres, like those of Neptune, but does not exclude the existence of more subtle and thin envelopes, like that of Mars. Another fascinating question is what kind of chemistry might dominate these atmospheres if they exist? Would they be rich in oxygen, like ours? Or perhaps have a toxic composition, similar to that of Venus? Scientists also wonder if these planets could experience extreme effects, such as unstable atmospheres that freeze on the night side and evaporate on the day side, a phenomenon possible because these worlds always show the same face to their star. This type of atmospheric dynamics leads us to imagine radically different climates from anything we know on Earth. In summary, the mystery of the atmospheres on the planets of Trappist-1 remains open. Although current technology has allowed us to rule out some scenarios, many questions still remain unanswered. Do these worlds hide thin but sufficient atmospheres to allow for life? Or are they arid and unprotected spheres? Solving this enigma will be essential to determine if any of these 7 siblings could, one day, be home to life as we know it, or to completely new and surprising forms. What happens when a star as small and cold as Trappist-1 illuminates its 7 planets? At first glance, we might think that the radiation from an ultra-cool dwarf poses little danger, but the reality is much more complex. Trappist-1, despite its relatively low temperature compared to the Sun, emits a significant amount of ultraviolet radiation and X-rays. Why is this important? Because this type of radiation can have dramatic effects on the atmosphere and surface of the planets that orbit close to it. The distance between Trappist-1 and its planets is incredibly small, especially when compared to the distances in our solar system. This means that, although the star is not as energetic as the Sun, its planets receive proportionally more high-energy radiation. Imagine living in a small house with a campfire in the center of the room. Even though the fire is small, the heat feels much more intense because the walls are close. In the same way, the proximity of the planets to Trappist-1 exposes them to stellar storms and sudden explosions that can alter the composition of their atmospheres in a matter of hours. Could this radiation hinder the development of life on any of these worlds? It's one of the great unknowns. Intense radiation can break down essential molecules, such as water, and strip away planetary atmospheres. On Earth, our magnetic field and thick atmosphere protect us from most harmful solar radiation. But on the planets of Trappist-1, is there any equivalent defense? The answer is still unclear, and it is precisely in these types of environments that astrobiologists seek the limits of habitability. Another intriguing question is whether the radiation from Trappist-1 could, paradoxically, play a positive role. On our own planet, radiation has been a driving force of evolution and has given rise to chemical processes fundamental to life. Could something similar happen on the planets of Trappist-1? Or on the contrary, would the radiation be so intense that it would prevent any form of complex life? The fascinating aspect of this system is that it forces us to rethink what we understand by habitable zones and shows us that life, if it exists out there, could be adapted to conditions that seem extreme to us. In summary, stellar radiation in Trappist-1 is a double-edged sword. It can be both an obstacle and a catalyst for life. Each new observation of this system brings us a little closer to understanding the delicate balances that make the emergence of life on other worlds possible or impossible. The key lies in discovering how much these planets can withstand the constant rain of energy and particles emitted by their small, yet restless, red star. What happens when 7 planets orbit so closely to each other around a tiny star? In the Trappist-1 system, the alignment of the planets is so precise that eclipses and transits are not only frequent, but occur with an almost choreographic regularity. It's like witnessing a dance where each planet crosses the path of the others in front of the star, casting shadows and momentarily blocking the starlight. But why is this so special compared to our own solar system, where eclipses are much rarer and harder to predict on such short timescales? The key lies in the extraordinarily compact arrangement of Trappist-1. The 7 planets orbit in such close proximity that, viewed from Earth, their transits are easily detectable. But if we were on one of those worlds, we would witness planetary eclipses several times in a single year. Imagine watching in the sky not only the transit of the star, but also the passage of other planets, creating brief sunsets and sunrises, or even causing night to fall abruptly in the middle of the day. Could these eclipses influence the climate or the perception of time on those planets? The eclipses in Trappist-1 are not just a visual spectacle. They also provide valuable clues about the dimensions and atmospheres of the planets. When a planet passes in front of another, or in front of the star, its atmosphere filters the light, allowing astronomers to analyze its composition from afar. This phenomenon is one of the most powerful tools for studying exoplanets, as each eclipse reveals information about density, the presence of clouds, or even the possibility of water. Could these eclipses be the key to finding signs of life on one of the sibling worlds? Moreover, the frequency and precision of these events in Trappist-1 help maintain the stability of the system, as the gravitational interactions that occur during alignments reinforce the planet's orbits. It's as if nature has synchronized the clocks of each planet so that they never miss a meeting. Thus, in the universe of Trappist-1, eclipses are not only an astronomical curiosity, but also a fundamental piece of the balance and harmony of a system that challenges our imagination. What would it be like to experience day and night on a Trappist-1 world? Unlike what we experience on Earth, where the sun rises and sets every 24 hours, on the planets of this system, the cycle of light and darkness could be completely different. In fact, many of these exoplanets are so close to their star and rotate in such a unique way that their days are eternal on one side and night is perpetual on the other. Why does this happen? The answer lies in a phenomenon called tidal locking. Tidal locking occurs when a planet always shows the same face to its star, just like the moon does with Earth. Can you imagine living in a place where the sun never sets, or conversely, where it is always night? In Trappist-1, this is a likely reality for several of its planets. The intense gravity of the star, combined with the proximity of these worlds, slows their rotation until it is synchronized with their orbit. Thus, one hemisphere receives constant starlight, while the other remains in perpetual shadows. But how does this affect the climate and the possibility of life? The eternal light on one side and the absolute darkness on the other create extreme conditions. One side may be exposed to continuous heat, while the night side can reach frigid temperatures. However, between both regions lies a band called the twilight zone, where daylight gently mixes with night, as if it were an endless sunset. This intermediate zone could be the most hospitable place for life, if it existed, as temperatures there would be more moderate. Could there be variations in these cycles? Some scientists believe that slight oscillations in the orbit or the tilt of the axis could allow certain areas to experience minor changes in light over time, although never as pronounced as our terrestrial days and nights. Ultimately, the cycle of day and night on Trappist-1 is a fascinating example of how celestial mechanics can create worlds radically different from what we know. Who could have imagined that, just 40 light-years away, there are planets where the sunset never ends? What really differentiates the Trappist-1 system from our own solar system? While both share the fascinating characteristic of hosting multiple planets, the similarities practically end there. To begin with, the central star of Trappist-1 is an ultra-cool dwarf, much smaller and dimmer than our Sun. If the Sun were a bonfire in the middle of the night, Trappist-1 would be barely a red ember. This means that the planets of Trappist-1 orbit much closer to their star to receive a similar amount of energy. Can you imagine if all the planets in the solar system were closer to the Sun than Mercury? That's how compact the worlds of Trappist-1 are. Another intriguing difference is the size and composition of the planets. While in the solar system there is a clear division between rocky planets like Earth, Mars, Venus, and Mercury, and gas giants like Jupiter and Saturn in Trappist-1, the 7 known planets are rocky and very similar in size to Earth. It's as if we took 7 alternative versions of Earth and placed them in close orbits to each other. Why are there no gas giants in Trappist-1? This question continues to intrigue astronomers and may be related to the initial formation conditions of the system. The orbital arrangement is also astonishingly different. While in the solar system the planets are spread out over great distances, in Trappist-1 the orbits are so close that, if we were there, we could see the other planets as large disks in the sky, much brighter than a full moon on Earth. Additionally, the planets of Trappist-1 are in orbital resonance, meaning their movements are synchronized in precise mathematical patterns. In contrast, the solar system is much less melodic, with less resonant orbits and more separation between its planets. Finally, time also plays in favor of the difference. A year on the outermost planet of Trappist-1 lasts just a few Earth days, while in the solar system, Neptune takes over 160 years to complete an orbit. This is due to the proximity of the planets to their star and the low mass of Trappist-1. So, while on Earth we celebrate a birthday every 365 days, on Trappist-1, we could celebrate it every week. This compact planetary dance, along with such distinct stellar conditions, makes Trappist-1 a unique natural laboratory radically different from the solar system we call home. Have you ever wondered what the distances between planets would be like if we lived in the Trappist-1 system? Unlike the solar system, where planets are separated by vast millions of kilometers, in Trappist-1, everything happens on much more compact scales. The 7 planets orbit their parent star in such a small space that if we placed them within Mercury's orbit, they would all fit comfortably. To give you an idea, the distance between Trappist-1 and its farthest planet, Trappist-1h, is less than the distance between the Sun and Mercury. This means that, in cosmic terms, the planets of Trappist-1 are close neighbors, almost as if they were houses on the same street, rather than countries on different continents. But how fast do these worlds orbit? While Earth takes a full year to go around the Sun, the planets of Trappist-1 complete their orbits in much shorter times. The planet closest to the star makes a complete orbit in just over a day and a half on Earth, and the farthest does so in less than 20 days. Imagine living in a place where years last less than a month on Earth. This accelerated pace means that sunrises, seasons, and orbital cycles would be completely different from what we know. Moreover, the scale of the orbits in Trappist-1 challenges our intuitions. If we reduce the solar system to the size of a soccer ball, the planets of Trappist-1 would be so close together that you could walk between them in a simple stroll. This proximity also means that from the surface of one of these planets, the others would be visible in the sky as huge spheres, much larger than the Moon as seen from Earth. Can you imagine looking up at the sky and seeing your sibling planets so close that you could distinguish details on their surfaces? Finally, the total distance separating the Trappist-1 system from Earth is about 40 light-years. Although this sounds far away, in astronomical terms, it's like our galactic neighborhood. If we traveled at the speed of light, it would take us 4 decades to get there. But with current technology, this journey would take hundreds of thousands of years. Still, the fact that we can study such a compact and distant system in such detail reminds us of how amazing our universe is, and how much we still have to discover about the scales and distances that govern it. What awaits us in the exploration of the Trappist-1 system in the coming years? Scientific curiosity knows no bounds, and currently, this system is one of the top priorities for several of the world's most advanced telescopes. Why so much attention? Because each new observation could completely change what we think we know about planet formation and the possibility of life beyond our solar system. Trappist-1 has become a natural laboratory for studying rocky exoplanets and their atmospheres, a true testing ground for modern astrobiology. Several eyes in space and on Earth are already focused on these 7 sibling worlds. The James Webb Space Telescope, with its impressive ability to analyze the composition of distant atmospheres, is ready to search for signs of water, methane, and other possible indications of chemical activity. Is it possible to detect the fingerprint of life on any of these planets? Scientists hope that, with the precision of the James Webb, they can distinguish layers of clouds, types of gases, and even traces of biological processes, if they exist. At the same time, ground-based telescopes like the VLT in Chile and the future Extremely Large Telescope plan to measure the masses, orbits, and temperatures of these exoplanets in greater detail. But can current technology really show us the surface of these worlds? We are still far from obtaining direct images, but new techniques, such as transit spectroscopy, allow us to analyze the light that passes through planetary atmospheres. It's like trying to deduce the flavor of a soup just by smelling the steam escaping from the pot. With each transit, astronomers gather clues about the presence of clouds, mists, and even possible oceans hidden beneath dense atmospheres. What if there were a planet with a water cycle similar to Earth's? In parallel, future missions like Ariel, specialized in the study of exoplanetary atmospheres, are in development and promise to further expand our knowledge of Trappist-1. Collaboration among international observatories will allow for the comparison of results, refinement of models, and discovery of patterns that could be invisible to a single instrument. Each new piece of data is another thread in the complex web of information that will gradually reveal the secrets of these distant worlds. Will any of them truly be habitable? Or will we discover completely new forms of planets, different from anything we know? The truth is that with each observation, we get a little closer to understanding our place in the universe. What role does the James Webb Space Telescope play in the study of the Trappist-1 worlds? To understand this, let's think about how, for centuries, humanity has observed the universe with increasingly precise tools, but always with limitations. Before the James Webb, telescopes could only provide us with blurry images and general data about these distant exoplanets. But now, the James Webb is like being given the key to open a direct window into the atmosphere and composition of these 7 sibling worlds. Is it possible to detect the atmosphere of a planet hundreds of trillions of kilometers away? Surprisingly, yes. The James Webb uses its ability to analyze the light that passes through the atmospheres of exoplanets as they cross in front of their star. It's as if we could smell the ingredients of a soup just by observing the light that passes through it. Thanks to its sensitivity in the infrared, it can identify the presence of molecules like water vapor, carbon dioxide, methane, or even hints of oxygen, fundamental elements to consider the possibility of life. But the James Webb doesn't just observe the atmosphere. It also measures tiny variations in the brightness of the star, allowing us to calculate the surface temperature of the planets, their composition, and even whether clouds or mists are present. What would it mean to find liquid water or a dense atmosphere? This would revolutionize our understanding of habitability beyond the solar system and transform Trappist-1 into one of the leading candidates in the search for life. Are we close to finding signs of life? Although there are still no definitive answers, the James Webb is gathering unprecedented data. Every time it points at Trappist-1, it's as if it's unraveling a new chapter of the great cosmic book. The coming decades promise even more astonishing discoveries thanks to this telescope, which turns what was once pure speculation into tangible and measurable science. The James Webb is undoubtedly humanity's great ally in exploring these distant worlds and in the eternal search for companionship in the universe. How is it possible to understand the behavior of such a complex system as Trappist-1, with 7 planets dancing around a tiny star? Scientists turn to simulations and computational models, tools that allow them to recreate step by step the evolution of this intriguing planetary system. Through these simulations, scenarios are explored that would be impossible to observe directly in reality. What would happen if one of the planets were slightly more massive, or if the orbits were a little more separated? This way, astronomers can test the laws of physics under exotic conditions and discover the surprising stability of Trappist-1. One of the most fascinating mysteries of this system is how it has managed to remain stable for billions of years despite the extreme proximity of its planets. Numerical models show that the key lies in orbital resonances, precise mathematical patterns that synchronize the movements of the planets, as if they were musicians playing in a perfectly coordinated orchestra. If a planet deviates, the gravity of its neighbors pushes it back into rhythm. However, these simulations also reveal how delicate this balance is. A small change in the mass or speed of one of the planets is enough for the system to become chaotic, and the sibling worlds end up being ejected or colliding. Simulations not only answer questions about the current stability, but also allow us to look back in time and ask, how did this compact system form? The most accepted theories suggest that the planets of Trappist-1 were born far from their star and gradually migrated inward, becoming trapped in resonances as they progressed. This process is like a complicated game of cosmic musical chairs, where each planet finds its exact place so that all can coexist in harmony. Computational models, by adjusting variables such as the temperature of the protoplanetary disk or the presence of other bodies, allow for the exploration of dozens of possible formation scenarios. However, despite advances in simulation, there are still open questions. How much do gravitational tides influence the internal structure of these planets? Could interactions between them provoke volcanic activity or even affect the presence of atmospheres? The latest models are beginning to incorporate increasingly realistic details, from the composition of the planets to the influence of stellar radiation. But, as in all science, each answer opens the door to new questions, showing that the Trappist-1 system remains a natural laboratory for understanding not only planetary dynamics, but also the possibilities of life on other worlds. How does such a peculiar planetary system as Trappist-1 come about? To answer this question, we must go back to the origins of the system itself, billions of years ago, when everything was a cold, dark cloud of interstellar gas and dust. This cloud, like the mass of a cosmic recipe, began to collapse under its own gravity, initiating a process of star formation that, instead of ending in a large star like our Sun, produced an ultra-cool dwarf and 7 planets very close to each other. Was it a usual process or something exceptional? Astronomers believe that the formation of Trappist-1 was, in many ways, different from that which gave rise to our solar system. Instead of an extensive protoplanetary disk, it is thought that the available material was limited and cold, favoring the emergence of small, rocky planets, all orbiting very close to their star. Unlike the gas giants we find in the solar system, here evolution favored the creation of compact worlds, comparable in size to Earth and Venus, but with orbits so tight that, if we placed them in our system, they would all fit within the orbit of Mercury. What role did planetary migrations play? According to theoretical models, the planets of Trappist-1 did not necessarily form in the positions where we find them today. They may have formed further out and subsequently migrated inward, gradually approaching the parent star. This phenomenon, known as planetary migration, occurs when planets interact with the gas and dust disk, as if they were trying to find balance on an orbital dance floor. The resonances observed today among the planets are a clue to these past movements, as if they were traces of an ancient choreography that still sets the rhythm of the system. Could the star itself have influenced the evolution of its planets? Being an ultra-cool dwarf, Trappist-1 has low luminosity and a much longer life than larger stars. This implies that the environment where the planets formed was less violent, allowing rocky worlds to retain some of their original atmosphere and water, if they had any. However, the extreme proximity to the star also poses challenges. Radiation and stellar wind may have altered the composition and structure of these planets over eons, sculpting a compact, synchronized, and at the same time, deeply mysterious system. The story of the formation of Trappist-1 is, ultimately, a window into the mechanisms that nature uses to create planetary systems very different from ours. How many other similar systems might there be in our galaxy? That is one of the big questions that keep science awake as we continue to explore the secrets of the cosmos. What would happen if we could stand on the surface of one of the Trappist-1 planets and look towards the horizon? Would we see clear skies, hellish storms, or perhaps eternal clouds covering the sky? The weather on these worlds remains a fascinating enigma for science, but current models and simulations allow us to imagine surprising scenarios. Given the proximity of these planets to their star, many of them, especially those located in the habitable zone, could experience extreme weather conditions, very different from anything we know on Earth. One of the keys to understanding the meteorology on Trappist-1 lies in the relationship between the planet and its star. Due to tidal locking, it is likely that most of these planets always show the same face to their sun, just as the Moon does with Earth. This peculiarity causes a radical thermal contrast. One hemisphere is constantly bathed in starlight, while the other remains in perpetual night. What does this mean in climatic terms? In the illuminated zone, we could find high temperatures and an atmosphere in constant motion, where winds attempt to redistribute heat towards the dark side, leading to supersonic storms and gigantic circulation patterns. Some scientists compare these winds to permanent hurricanes, much more powerful than any terrestrial cyclone. But are there clouds on these exoplanets? Simulations suggest that yes, although not necessarily formed by water as on our planet. Depending on the atmospheric composition of each world, we might find clouds of mineral particles, or even exotic compounds like carbon dioxide or methane. These clouds would not only affect surface temperature, but also the appearance of the sky and the amount of light reaching the ground. On some planets, cloud cover could be so dense that the surface would receive barely a permanent twilight, while on others, the nighttime side could be covered in ice or frost, a result of the condensation of atmospheric gases. Of course, the most intriguing question is whether any of these planets could have hydrological cycles similar to those on Earth. If there is water on the surface or in the atmosphere, we could observe rain, fog, or even liquid oceans in the intermediate zones, where heat and cold balance each other. However, the intensity of storms, the possibility of extreme winds, and the presence of habitable zones will depend on factors not yet fully understood, such as the exact composition of each atmosphere and its interaction with stellar radiation. Meteorology on Trappist-1 is, ultimately, a natural laboratory where physical laws create landscapes and climates much more varied and extreme than we could imagine in our own world. What secrets can worlds we have never set foot on hide? When we talk about planetary geology in the Trappist-1 system, we face a true cosmic puzzle. The 7 planets orbiting this ultra-cool dwarf star are mostly rocky, but how do we know this if we have never received a stone from those worlds? Scientists have managed to deduce the solid nature of these planets thanks to the precise measurement of their masses and radii. By comparing these values, it is discovered that their density is similar to that of Earth and Venus, indicating that they are primarily composed of rocky materials, such as silicate and iron. It's as if we are observing a group of gems hidden in the darkness, trying to guess their composition based on their shine and weight. Could these planets have mountains, volcanoes, or even continents? Although there is still no way to directly photograph their surfaces, scientific models suggest that, like Earth, they could harbor significant geological activity. The tidal forces generated by the proximity between the planets and their star are so intense that they could heat the interiors of these worlds, causing volcanism and tectonic movements. An example in our own system is Io, Jupiter's moon, famous for its active volcanoes due to tidal forces. Thus, it would not be far-fetched to think that Trappist-1 has incredible landscapes, with volcanic regions and terrains as varied as those of Earth or Mars. And what about the crust and core of these exoplanets? Current calculations indicate that many of them could have metallic cores, likely rich in iron, surrounded by rocky mantles. Some might even have underground oceans, trapped beneath layers of ice or rock, like Europa, Jupiter's moon. This possibility is particularly intriguing because where there is liquid water, even if it is beneath the surface, the likelihood of complex chemical processes increases, perhaps even life. Furthermore, if tectonic plates exist, they could recycle nutrients and form dynamic landscapes, facilitating the evolution of ecosystems. However, not everything is certain. The geology of these planets remains an enigma in many aspects. Is the surface covered with rocky deserts, seas of lava, or perhaps vast frozen oceans? Are there atmospheres that erode mountains, or winds that sculpt valleys? Each of these questions reminds us of how much we have yet to discover. The fascinating aspect of planetary geology in Trappist-1 is that each new piece of data could completely change our image of these distant worlds, challenging what we think we know about the formation and evolution of rocky planets in the universe. What would happen if 7 Earth-sized planets were so close to each other that, Instead of feeling like lonely islands in the cosmic ocean, they lived in a bustling and energetic neighborhood. That's exactly what happens in the Trappist-1 system. Unlike the planets in our solar system, which are separated by vast distances, the worlds of Trappist-1 are so close that their gravitational interactions play a fundamental role in their orbital dynamics. But how do these forces affect the stability and potential life of these exoplanets? To understand this, it's helpful to imagine the planets as dancers on a very crowded dance floor. Each one moves to its own rhythm, but at the same time, it must coordinate with the steps of its neighbors to avoid collisions. In Trappist-1, the gravity of each planet constantly pulls on the others, slightly altering their orbits in a kind of cosmic choreography. These gravitational tugs make the planets vibrate, speed up or slow down, maintaining a sort of dynamic equilibrium. The result, a surprising stability, but also an extreme sensitivity to any changes in the system. One fascinating aspect of these interactions is that they generate very precise orbital resonances. That is, for every exact number of orbits that one of the planets makes around the star, its siblings also complete a specific number of orbits. This phenomenon, far from being coincidental, is the invisible glue that keeps order in the system. If one of these orbits were to be altered, even slightly, the harmony could break, causing instability and, in the worst case, the ejection of a planet from the system. This millimeter-precise dance allows the planets to remain together for billions of years. But these forces go beyond simple orbital stability. Gravitational interactions could also influence fundamental aspects of habitability. For example, the tidal forces generated by the proximity of the planets can heat their interiors, as happens with Jupiter's moons, altering their geology and the possibility of maintaining dense atmospheres or even underground oceans. This raises an intriguing question. Could these same forces, so intense, be a blessing for life by maintaining internal energy, or a curse by causing instability and extreme conditions? In short, the gravitational interactions in Trappist-1 transform this system into a unique natural laboratory, where the physics of planetary dance manifests in its fullest expression. Each planet is both an actor and a spectator of a delicate and impressive balance that challenges our traditional ideas about the architecture of solar systems. The complexity of these relationships remains a subject of study, with the hope that by understanding them better, we can decipher not only the secrets of Trappist-1, but also those of other systems in our galaxy. What are the real chances of finding life on the worlds of Trappist-1? This question has fascinated scientists and enthusiasts alike, and rightly so. With 7 Earth-sized planets all orbiting an ultra-cool dwarf star, the system presents an exceptional natural laboratory to investigate whether life, as we know it, could arise beyond our own planet. But what minimum conditions are needed for life to emerge? Primarily, the presence of liquid water, a stable energy source, and an atmosphere that protects and regulates the environment. Trappist-1 offers intriguing scenarios where these conditions could be met, at least in theory. Could some of these planets harbor oceans beneath strange skies? The possibility exists, especially on those planets located in the so-called habitable zone, where temperatures would allow for the existence of liquid water on the surface. Scientific models suggest that Trappist-1e and Trappist-1f are the most promising candidates, as they receive enough energy from their star to avoid total freezing, but not so much as to boil their seas if they have any. However, life does not only depend on the distance from the star. Atmospheric composition is key. If these planets have dense and stable atmospheres, they could maintain mild temperatures over long periods, favoring the chemical processes necessary for life. But what kind of life could we find there? Would it be familiar forms like Earth bacteria or something completely different? Life, as we know it, is based on carbon and water. However, in extreme environments on Earth, such as deep-sea vents or frozen deserts, there are creatures capable of surviving under pressures, temperatures, and radiations far beyond the norm. This opens up the possibility that if life exists on Trappist-1, it could be resilient and adapted to conditions that would seem lethal to us. Moreover, the proximity between the planets could allow for the exchange of materials, such as meteorites, carrying microorganisms and favoring panspermia, the hypothesis that life can travel between worlds. To what extent can the planets of Trappist-1 protect themselves from stellar radiation and maintain the atmosphere necessary for life? The central star is an ultra-cool dwarf, much less luminous than the Sun, but it can emit flares and radiation that could erode the atmospheres of its planets. If these worlds have powerful magnetic fields, similar to Earth's, they could protect their surfaces and maintain habitable environments for millions of years. However, the existence or absence of these magnetic fields is, for now, an unknown. The search for life on Trappist-1 is ultimately an exploration of the limits of biology and astrophysics, an invitation to ask ourselves whether life is a rarity or an inevitable consequence when the conditions are right. What are the true obstacles that life faces to emerge and survive on the planets of Trappist-1? At first glance, finding a system with so many rocky worlds in the habitable zone seems like an irresistible invitation for life. However, the environment of Trappist-1 poses extreme challenges that test even the most resilient organisms we can imagine. One of the most serious problems is the intense ultraviolet and particle radiation emitted by its parent star, an ultra-cool dwarf that, despite its name, is surprisingly active. Stellar flares can be frequent and violent, bombarding the planets with radiation capable of destroying organic molecules and potentially stripping the worlds of their protective atmospheres. Can an atmosphere survive in such a hostile environment? The answer is not straightforward. If the planets of Trappist-1 lack strong magnetic fields, it is likely that stellar radiation will slowly erode their atmospheres, leaving the surfaces exposed and barren. Imagine trying to build a sandcastle on the shore while the waves relentlessly crash against it. That is how vulnerable an atmosphere would be without protection from stellar winds. Even if a dense atmosphere existed, a key question is its composition. Would it contain the right gases to maintain liquid water and allow biological processes, or would it be toxic and unbreathable for any form of terrestrial life? Surface temperature is another monumental obstacle. Although some planets are located in the so-called habitable zone, where liquid water could exist, the reality is that conditions can vary drastically between the day and night sides due to tidal locking. Many of these worlds always show the same face to their star, resulting in a scorching hemisphere and a frozen one. Could life adapt to a world where the eternal day burns and the perpetual night freezes? Perhaps only in a narrow twilight band, between light and shadow, could more stable conditions arise. But even there, survival would be a feat. Moreover, the availability of water is uncertain. Although some models suggest the presence of ice or underground water, there is no definitive evidence of its existence in liquid form on the surface. Without stable and accessible water, life as we know it would face insurmountable difficulties in developing. Added to this, the lack of essential nutrients and the possible presence of hostile chemical compounds further complicate the picture. Thus, while Trappist-1 is a fascinating natural laboratory, life there would have to overcome much harsher barriers than on Earth, facing an environment that tests the limits of biology and imagination. How far is Trappist-1 really? At first glance, we might think that in the universe everything is just around the corner, but the reality is overwhelming. Trappist-1 is located nearly 40 light-years from Earth, a distance that, in cosmic terms, is relatively close, but for human technology represents an almost insurmountable abyss. If we wanted to make a trip there using the fastest spacecraft ever built by humanity, Voyager 1, it would take us over 600,000 years. That is, if our ancestors had started the journey when they were still drawing bison in caves, there would still be thousands of generations left to arrive. Is there then any realistic possibility for humanity to explore Trappist-1 in person? With current physics, the answer is a resounding no. conventional propulsion methods, based on chemical fuels, have barely allowed us to leave our solar neighborhood. Even the most advanced technologies we can imagine, such as ion propulsion or fusion engines, would reduce the travel time to tens of thousands of years. It's like trying to row across the Atlantic when we are just learning to swim. The barrier of the speed of light imposes an unbreakable limit. Nothing with mass can reach it, much less exceed it. This places planetary systems like Trappist-1 in the category of unreachable destinations, at least for now. However, human curiosity knows no bounds, and scientists are already exploring revolutionary alternatives. One of the most ambitious ideas is the use of solar sails propelled by giant lasers from Earth. In theory, these small probes could reach a significant fraction of the speed of light, completing the journey in a few decades. But this type of project faces titanic challenges, from the extreme miniaturization of the spacecraft to resistance to interstellar radiation and the precision of navigation over inconceivable distances. Each obstacle is as colossal as the distance to be traveled, but no less fascinating. And what about the possibility of sending humans? Here, science fiction often takes over, with concepts like generation ships where several generations would be born and die during the journey, or cryogenic hibernation to sleep for centuries. But these scenarios, for now, belong more to the realm of imagination than practical engineering. Still, thinking about interstellar travel forces us to ask, will it ever be possible to cross the void between the stars? Every new advance, no matter how small, brings us closer to turning the impossible into a mere question of time. Until then, Trappist-1 will remain a distant beacon, a reminder of the titanic challenges that await human exploration beyond the solar system. What is it about Trappist-1 that has captured the imagination of writers, filmmakers, and science fiction fans around the world? Perhaps the answer lies in its astonishing resemblance to a miniature solar system, where 7 rocky worlds orbit a tiny, cold star. This unusual configuration has inspired stories that dream of alien civilizations, human colonies, and mysteries yet to be discovered. Trappist-1 has become a symbol of the infinite possibilities that exist beyond our own cosmic neighborhood, like a kind of stellar neighborhood that many would wish to move to in the distant future. In literature, Trappist-1 has appeared in contemporary science fiction novels that explore interstellar migration and the challenges of adapting to new worlds. What kind of societies could arise in a system where sunrises and sunsets are marked by the constant passage of other planets in the sky? Authors take advantage of the compact arrangement and resonance between the worlds to imagine interplanetary cultures, frequent travel between sibling planets, and even geopolitical conflicts on a stellar scale. The real characteristics of these exoplanets fuel plots in which life, if it exists, must be as resilient and adaptable as it is unique. Film and television have also turned Trappist-1 into a backdrop for space adventures. Have you ever stopped to think about why so many screenwriters choose systems like this to set stories of exploration and alien contact? The reason is twofold. On one hand, the scientific mystery surrounding these planets offers a blank canvas. On the other, the proximity between the worlds allows for the imagining of quick travels and the possibility of observing other habitable lands with the naked eye, something that is unthinkable in our solar system. Movies, video games, and documentaries have recreated Trappist-1 as a place where humanity could establish its first home beyond Earth, or where we might encounter life forms completely different from what we know. Even outside of fiction, Trappist-1 has become a cultural phenomenon. Why does this system, among so many discovered, ignite the hope and curiosity of the public? Perhaps because it represents the frontier of what is possible. It shows that systems with multiple rocky planets, some potentially habitable, are not exclusive to our star. It has inspired illustrations, digital artworks, debates in forums, and even songs that evoke the longing to explore the unknown. Trappist-1, in short, is much more than a set of astronomical data. It is a collective invitation to dream of new worlds and to imagine our place in the universe. What makes the Trappist-1 system so special in the search for exoplanets? To understand its impact, we must first remember that for a long time, astronomers could only dream of discovering Earth-like worlds outside our solar system. Trappist-1 radically changed that landscape. Suddenly we found not one, but 7 rocky planets orbiting a single star, several of them in the habitable zone. This finding demonstrated that not only can solar systems have planets with potential for life, but that such configurations could be much more common than we imagined. What if systems filled with rocky planets were the norm rather than the exception in our galaxy? The revolution sparked by Trappist-1 was comparable to finding an archipelago of unknown islands in the midst of an immense ocean. Before this discovery, astronomers had already identified hundreds of exoplanets, but most were gas giants or extreme worlds. Trappist-1 shifted the focus to small, temperate planets, expanding the boundaries of what we consider possible in planetary system formation. Moreover, this system demonstrated the effectiveness of the transit method for detecting planets, even around tiny, cool stars, opening the door to explore thousands of red dwarfs in search of similar systems. To what extent did Trappist-1 change the priorities of astrophysics? Since its discovery, telescopes and observational projects have adjusted their strategies, dedicating more time to searching for planets around small, cool stars. As these systems seem to be more abundant and perhaps more accessible for detailed studies of their atmospheres, Trappist-1 became the perfect example of what astrobiology seeks: potentially habitable planets aligned in such a way that we can analyze their composition, climate, and even signs of life with current and future tools. Another key consequence of the impact of Trappist-1 is the inspiration it generated in the scientific community and the general public. Why is the idea of 7 sibling worlds so close to each other so exciting? Because it suggests that planetary diversity is not something rare, but part of the very fabric of the cosmos. Each exoplanet found in Trappist-1 is an invitation to rethink our ideas about planet formation, their ability to harbor water, and the real possibility of life beyond Earth. In summary, Trappist-1 not only expanded the map of the search for exoplanets, but also made us reconsider what it means to be a habitable world and how many more might be waiting to be discovered in the vast universe. Have you ever wondered how it would be possible to unravel the secrets of a planetary system as complex as Trappist-1? The answer does not lie with a single person or a single observatory, but in a network of scientific collaborations spread across the globe. Trappist-1 has become a perfect example of how modern astronomy demands the union of international efforts, where teams from different countries, universities, and space agencies pool resources, technology, and knowledge with a common goal: to understand the nature of these 7 sibling worlds. This global synergy is fundamental for the simple reason that no telescope, no matter how advanced, can study all aspects of such a distant and complex system on its own. So how do scientists coordinate? Imagine an orchestra, where each instrument contributes a unique note to create a melody that would be impossible to achieve alone. Similarly, astronomers in Europe, America, Asia, and other continents divide tasks. Some monitor planetary transits, others analyze light spectra in search of atmospheres, and some develop mathematical models to simulate orbital evolution. Additionally, they share all their data through open networks, allowing independent teams to validate or refine findings, increasing the reliability of the results. Who participates in this gigantic endeavor? From institutions like NASA and the European Space Agency, to university observatories and international consortia of ground-based and space telescopes. Even amateur scientists have played a significant role, detecting variations in the brightness of Trappist-1 and alerting the professional community. This constant flow of information and cross-observations has been key to discovering, for example, the exact resonance between the orbits of the planets. or to ruling out potential false signals that could confuse the data. The impact of these collaborations goes far beyond the study of Trappist-1. Each discovery, each perfected technique, and each challenge overcome in this system is shared almost instantly with the global scientific community, accelerating the search for exoplanets in general. By working together, astronomers multiply their analytical and creative capacity, tackling technical and theoretical challenges that would be insurmountable for an isolated team. Thus, Trappist-1 becomes not only a natural laboratory for the study of planetary habitability, but also a symbol of what humanity can achieve when it unites its curiosity and ingenuity in the quest for cosmic answers. What secrets does the Trappist-1 system still hide? Although astronomy has made giant strides in its study, there are still fascinating questions that keep the scientific community on edge. For example, do these planets really have stable atmospheres? Or has the constant bombardment of radiation from their parent star faded them over time? The presence of an atmosphere could make the difference between a dry, barren world and one capable of harboring the basic ingredients for life. Current observations have only just begun to scratch the surface of this mystery. Another intriguing question is the exact composition of the surface of these planets. Are they rocky deserts, endless oceans, or completely alien landscapes? Data suggests that several of them could have a density similar to that of Earth. But what materials dominate their crust and mantle? For scientists, each planet in Trappist-1 is like a locked safe with a combination. Each turn of the dial represents a new hypothesis about volcanism, tectonic plates, or even the existence of geysers of water or ice. Could any of these worlds hide a global ocean beneath their surface, as some moons in our own solar system do? Orbital synchronization is another piece of the puzzle. If the planets are trapped in such precise resonances, how does this affect their long-term stability? Is it possible that, on cosmic timescales, these compact orbits could crumble, or, on the contrary, remain stable for billions of years? This gravitational dance could influence not only the dynamics of each planet but also their climate and the possibility of seasonal cycles, storms, or even migrations of atmospheres and oceans. The question is, what would the climate patterns be like in such a tight and synchronized system? And of course, the most captivating question of all, is there life on any of these worlds? Although scientists have not yet detected direct signals, the possibility of microbial biospheres, or even more complex forms of life, cannot be dismissed. Could life have emerged under conditions so different from those on Earth? And if it exists, would it be able to adapt to the dim, reddish light of an ultra-cool dwarf star, or to the constant variations in temperature and radiation? Each answer obtained opens the door to new doubts, and Trappist-1 remains one of the most promising and mysterious scenarios for the search for life beyond our world. What does the future hold for Trappist-1? This question resonates among astronomers and dreamers around the world. The system, with its 7 rocky planets orbiting an ultra-cool dwarf star, represents one of the most fascinating natural laboratories for studying planetary evolution beyond the solar system. But how will these worlds evolve over the next tens of millions of years? And what role will they play in the search for life beyond Earth? The star Trappist-1 is young in cosmic terms, and as a red dwarf, it has a much longer expected lifespan than the Sun. This means that the planets orbiting it will have plenty of time to develop geological, atmospheric, and even theoretically, biological processes. Unlike more massive stars that consume their fuel in just a few 100 million years, Trappist-1 could shine for trillions of years. This extensive period offers a unique scenario. If life were ever to develop on any of these planets, it would have far more time to evolve and adapt, far surpassing the timescale we know on Earth. Could these planets change drastically over time? The gravitational interactions among the 7 worlds, due to their extraordinary proximity, could significantly alter their orbits and climates. Imagine a planetary system where gravitational pulls are constant, almost like a precise yet dynamic choreography. These interactions could, for example, cause internal heating through what is known as tidal heating, maintaining volcanic activity, or even facilitating the persistence of atmospheres for millions of years. However, there is also the risk that these same effects could end up destabilizing one of the planets or altering their surface conditions in unpredictable ways. The observation and study of Trappist-1 will continue to be fundamental for astrobiology and planetary science. With the arrival of even more powerful telescopes and specific missions in the future, we could obtain direct data on the composition of their atmospheres, the presence of organic compounds, or even indirect signals of biological activity. Trappist-1 could become the first system where clear signs of life beyond the solar system are detected, or it could serve as an example of how life can be extremely rare, even in seemingly favorable conditions. Ultimately, the fate of Trappist-1 and its 7 worlds remains open, filled with possibilities and mysteries. As technology advances and our ability to observe the cosmos expands, this small stellar system could reveal fundamental secrets about planet formation, the persistence of atmospheres, and the existence of life in the universe. Will Trappist-1 be the opening chapter of a new era in cosmic exploration? The answer, for now, remains waiting among the stars. What makes Trappist-1 one of the jewels of modern astronomy? The answer lies in its 7 sibling worlds, aligned like pearls on a cosmic necklace, orbiting a tiny yet mysterious star. Each planet, while similar in size to Earth, hides unique conditions, challenges, and potentials that defy what we thought possible about life beyond our solar system. Could the combination of compact orbits, perfect resonances, and positions within the habitable zone be the ideal recipe for the existence of water and even life? The Trappist-1 system has shown that our galactic neighborhood can be much more diverse and fascinating than we imagined. If we find 7 rocky planets in a single system, some in the region where liquid water could exist, how many other similar systems are waiting to be discovered? Trappist-1 acts as a kind of natural laboratory, where scientists can study planetary evolution, the influence of stellar radiation, and the formation of atmospheres, all in a compact and synchronized environment like a clock. However, the most important questions remain unanswered. Does any of these worlds truly possess a stable and protective atmosphere? Do the extreme conditions of radiation and tidal locking allow for the formation and persistence of liquid water? What surprises does the climate of these exoplanets hold? And what will the next data obtained by cutting-edge telescopes reveal? The answers to these mysteries could revolutionize our understanding of life in the universe and bring us, if only a little, closer to answering the eternal question, are we alone? The impact of Trappist-1 goes far beyond science. This system inspires entire generations to look at the sky with wonder and curiosity. It reminds us that, although the universe is vast and sometimes bewildering, it is also filled with opportunities to discover the unexpected. Thus, Trappist-1 becomes not only an object of study, but also a symbol of the human quest to understand our place in the cosmos, an invitation to continue exploring, questioning, and dreaming of the worlds yet to be discovered.